We introduce HexTiles, a domain-agnostic hexagonal-tiling-based visual encoding design for multivariate geospatial data. This design aims to simplify the process of interpreting interactions between multivariate geospatial data by placing the visualization designer in the driver's seat to guide user attention to specific variables and interactions. HexTiles explicitly mitigate the effects of the Modifiable Areal Unit Problem, MAUP, by proposing a confidence encoding for each information channel. The approach is validated through a user study and domain expert feedback from ecologists and hydrologists. Combining visualizations is a crucial aspect of data analysis, and various methods have been employed to achieve this. Two prominent approaches are juxtaposition and superimposition. Juxtaposition involves displaying multiple data channels in separate visualization instances, which can be effective but may lead to clutter with a large number of views. In contrast, superimposition displays multiple data channels in the same visualization instance, such as through layering and glyphs. Layering combines two or more conventional encodings on top of each other, while glyphs are used to encode multivariate data. However, these methods have limitations, including the need to reduce visual clutter and the importance of careful visual encoding. Another approach is the use of cartograms, which can be effective but inherently distort the base map. To address these limitations, the design of HexTiles, a novel superimposition-based visualization, is motivated by the need to faithfully visualize geospatial data of varying spatial discretizations. HexTiles aims to ease the process of assessing interactions between variables across spatial regions. By doing so, it provides a unique approach to combining visualizations, allowing for a more comprehensive understanding of complex datasets. Visualizing multivariate geospatial data poses significant challenges, particularly when conveying complex spatial distributions. Spatial binning, a technique that partitions data into discrete regions, offers a solution. However, the choice of tessellation shape significantly impacts the effectiveness of spatial binning. Hexagonal tessellations are preferred over square ones due to their ability to smoothly convey spatial distributions, minimizing artifacts and preserving local patterns. To further enhance the visualization of multivariate geospatial data, icons can be employed to leverage pre-attentive processing and reduce reliance on color maps. By using icons to represent unmet water demand data, for instance, complex information can be effectively conveyed. This approach enables the encoding of multiple variables into a single visual representation, facilitating a more comprehensive understanding of the data. A critical consideration in geospatial data analysis is the Modifiable Areal Unit Problem, MAUP, which arises from the arbitrary definition of spatial units. To address this issue, confidence encoding is proposed. This involves calculating a spatially weighted variance for each variable and expressing it through various visual elements, such as palette, ring thickness, and opacity. By incorporating confidence encoding, the uncertainty associated with spatial units is explicitly conveyed, enabling a more informed analysis of geospatial data. This approach has significant implications for the accurate interpretation and decision-making based on multivariate geospatial data. The HexTiles design is a visualization encoding method that addresses the Modifiable Areal Unit Problem, or MAUP, by incorporating a weighted variance to quantify confidence in geospatial data points. This approach leverages the hierarchical hexagon-based spatial binning system, H3, and WebGL accelerated DEC.gl for implementation. The HexTiles workflow consists of two primary stages: data aggregation and data encoding. In data aggregation, data points within a hex region are combined into a single aggregate data point. Subsequently, in data encoding, these aggregate data points are mapped to distinct HexTile components. The selection of data attributes for each HexTile characteristic is critical, as it significantly impacts the intuitiveness of the resulting visualization. To demonstrate the effectiveness of HexTiles, the authors present case studies utilizing diverse datasets, including 2020 presidential election and demographics data in Texas, as well as outputs from the California Water Resources Simulation Model, CalSim3. These case studies showcase the potential of HexTiles in facilitating the visualization of complex geospatial data, while mitigating the limitations imposed by the Modifiable Areal Unit Problem. The authors present a visualization framework for encoding variance in multivariate data using HexTiles, a novel visualization technique. The HexTile encoding workflow is illustrated in Figure 6, where the base color, semantic icons, and inner ring thickness are used to represent different data variables. The authors provide guidelines for choosing the mapping between data variables and HexTile components in Table 1. The framework is applied to two use cases: the 2020 presidential election data visualization in Texas and water distribution visualization from CalSim 3. For the election data, the authors visualize the % Democrat lead, % people of color, and population density using square glyphs, HexTiles without variance encoding, and HexTiles with variance encoding. The resulting visualizations are shown in Figures 7 and 8. For the water distribution data, the authors visualize unmet water demand, difference in unmet water demand with respect to historical baselines, and groundwater levels using the same visualization techniques. The resulting visualizations are shown in Figure 10. The authors highlight the importance of variance encoding in alleviating the Modifiable Areal Unit Problem, which occurs when the choice of spatial aggregation unit affects the results. They demonstrate this using the election data in Figure 9, where the variance encoding reveals a diverse mix of areas with varying levels of Democrat-led and % people of color near Dallas, Texas. This insight is absent without the variance encoding. The author's approach enables a more faithful representation of the data, allowing users to identify patterns and relationships that would be obscured by traditional visualization techniques. Figures 7 and 8 visualize the 2020 presidential election and demographics data in Texas and Houston, respectively. Figure 7 displays 6 visualizations, including population density, % people of color, and % Democratic-led. Additionally, it showcases 3 visualizations of these variables using square glyphs and HexTiles, both with and without variance encoding. Figure 8 focuses on the Houston data, encoding the 3 variables in square glyphs, HexTiles without variance encoding, and HexTiles with variance encoding. To assess the effectiveness of their HexTiles design, the authors employ a comprehensive evaluation methodology. This involves a user study with 7 participants, comprising 2 males and 5 females with varying levels of exposure to visualization. The participants include 5 PhD students, 1 Mega Siemens student, and 1 BS student. The study consists of 2 tasks: measuring accuracy and time to insight. An expert review with 3 domain experts supplements the user study, providing additional context and validation of the findings. The user study aims to investigate the efficacy of the HexTiles design in facilitating accurate and efficient insights into the data. The inclusion of domain experts in the expert review provides a more comprehensive understanding of the results. The author's evaluation approach incorporates both quantitative and qualitative measures, ensuring a robust assessment of their proposed visualization technique. This multifaceted approach enables a thorough examination of the HexTiles design's ability to support accurate and timely insights into complex data. The authors present a visualization comparison between HexTiles and square glyphs, a superimposition-based method, using the 2020 presidential election and demographics data. Figure 9 showcases the same region of the election data near Dallas, Texas, encoded in HexTiles with and without variance encoding, as well as at a higher zoom level. This visualization demonstrates the spatial hierarchy of HexTiles, where the hexagonal region approximately subdivides into 7 smaller hexagonal regions. Figure 10 displays the CalSim 3 output for a particular water allocation scenario at a particular time step. The figure comprises 6 visualizations: unmet water demand at each demand unit, the difference of unmet water demand with respect to historical baselines, groundwater levels, and 3 visualizations of the 3 variables square glyphs, HexTiles without variance encoding, and HexTiles with variance encoding. The HexTiles visualizations effectively capture the spatial relationships and variability in the data, whereas the square glyphs visualization struggles to convey this information. The comparison highlights the advantages of HexTiles in encoding and visualizing complex, high-dimensional data, particularly in capturing spatial relationships and variability. The use of variance encoding in HexTiles further enhances its ability to convey nuanced information in the data. The results underscore the potential of HexTiles as a valuable tool for exploratory data analysis and visualization, outperforming the existing superimposition-based method, square glyphs. The performance metrics and user feedback for two tasks involving HexTiles and square glyphs are discussed. Task 1 requires estimating the value of an encoded variable, while Task 2 involves finding a tile that satisfies specific conditions. Results indicate lower error rates and shorter time to insight for HexTiles compared to square glyphs, although these differences are not statistically significant. Participants found HexTiles easier to interpret, particularly due to the use of color, which was considered more intuitive than size in square glyphs. NASATLX survey results favor HexTiles across all categories, highlighting the advantage of color encoding in terms of usability and mental load. The HexTiles design offers a novel superimposition-based visualization for multivariate geospatial data, showcasing its effectiveness in communicating data with a lower mental load compared to square glyphs. It incorporates semantic icons to guide user attention to specific variables. User studies and expert reviews highlight HexTiles' ability to convey patterns over larger regions, particularly in water resource management. While limitations include color interactions, visual complexity, levels of abstraction, and occlusion of underlying terrain, HexTiles excel in showing general patterns of multivariate data, making it suitable for urban areas and regions between urban areas. HexTiles, a novel multivariate geospatial data visualization technique, has garnered significant feedback from domain experts, who have attested to its effectiveness in facilitating the exploration and analysis of complex geospatial data. This feedback highlights the technique's ability to efficiently convey multivariate relationships and patterns in a spatially aware manner. However, the superimposition-based design of HexTiles also presents inherent limitations. For instance, the technique's reliance on superimposition can lead to visual occlusion, making it challenging to discern individual variable contributions to the overall pattern. Furthermore, the fixed hexagonal resolution can result in information loss and visual clutter, particularly when dealing with high-dimensional data. To address these limitations, future work will focus on exploring the usability of HexTiles for data encoding, enabling more efficient representation of multivariate data. Additionally, adaptive task-based hexagonal resolution will be investigated, allowing for dynamic adjustments to the resolution based on the analytical task at hand. Another key area of exploration will be the incorporation of temporal data, enabling the visualization of spatio-temporal patterns and relationships. By addressing these limitations and expanding the capabilities of HexTiles, researchers can unlock the full potential of this innovative visualization technique, ultimately enhancing our ability to extract insights from complex geospatial data. Geographic data visualization is a crucial aspect of understanding complex spatial relationships. This field encompasses various techniques, including bivariate geostatistical data visualization, cartograms, and multivariate scalar data visualization over geographic maps. Bivariate geostatistical data visualization involves the representation of two variables, such as temperature and precipitation, across a geographic region. This type of visualization enables researchers to identify spatial patterns and correlations between the variables. Cartograms, on the other hand, are a specific type of visualization that distorts the shape and size of geographic regions to convey quantitative information. For instance, a cartogram might depict population density by scaling the size of each region proportionally to its population. This technique allows for the efficient communication of complex data insights. Multivariate scalar data visualization over geographic maps involves the representation of multiple variables, such as demographic, environmental, and economic data, on a single map. This approach enables researchers to identify intricate relationships between variables and their spatial distributions. To achieve this, researchers employ techniques such as choropleth mapping, which assigns different colors to regions based on the values of the variables. Effective geographic data visualization is contingent upon the careful selection of visualization methods, as different techniques can convey distinct insights. Furthermore, the integration of interactive and dynamic visualization tools can facilitate the exploration of complex datasets. However, it is essential to acknowledge the limitations of geographic data visualization, including issues related to data quality, spatial autocorrelation, and the potential for misinterpretation. Future research directions in this field include the development of more sophisticated visualization techniques, the integration of machine learning algorithms to identify complex patterns, and the exploration of immersive visualization environments. By advancing the field of geographic data visualization, researchers can unlock new insights into the complex relationships that shape our world.